Let's look at a inverse Laplace transform problem, and in this particular case, this is problem 42 in chapter 12, part A. If you look at this transform, it actually has the numerator and denominator polynomial having the equal order, and for that reason we need to divide the denominator polynomial into the numerator polynomial to get a piece of that transform to be proper. And the calculator is ideal for that. In this case, we're using the TI-89 titanium, and what we are going to do is the very first command that we will issue is this proper frac command within the calculator. If I turn that on, and I'm now lined up on the home screen, I'll press enter to get to the command line. I'll go into the catalog of functions and try to get down to the P by hitting the key that's associated with the P. And in order to scroll down quickly, I can do second down arrow, and you can see hopefully that proper frac is the bottom command or bottom function in that window. I can go one beyond that by hitting the second down arrow and click just up one. Now I have the proper frac. I'll hit enter. That's now on my command line. I can now input the expression, and I'll put the numerator inside parentheses and divide that by the denominator that will also be inside parentheses. I will now say left parenthesis 5x squared. I'm using x instead of s because x is a key right there on the front of the calculator, plus 38x plus 80. That's my numerator. I'll close that parenthesis. I'm going to divide that now by the denominator, which I now open up another parenthesis, and I have x squared, x caret 2, plus 6x plus 8. I'll close the denominator. I'll close the function proper frac, hit the enter key, and now I have capital F of s as 5 plus, and now I have the isolated proper fraction that I was looking for, 8s plus 5 over s squared plus 6s plus 8. What I want to do now is work with inverse Laplace transforming or finding the partial fraction expansion of this proper fraction piece. And maybe what I want to do is first determine what the denominator polynomial looks like in terms of its factors. If those are real roots, I can use the factor function inside the calculator, and for that reason then let me go ahead and clear this input line so that you can see what I'm doing. I'm going to actually go up with the cursor and obtain that expression, the entire capital F of s expression, and I'm going to copy it down into the command line. Fortunately for us, the plus 5 is on the right side. I'm going to backspace through those to cancel that because I do not want to do the partial fraction expansion with the 5 in the formula. Now I want to go to the leftmost part, so I hit the second left cursor sequence, and I'll go into the catalog of commands. I will tap the F key, and that actually gets me to the factor formula immediately, or the function factor. I'll hit enter to bring that in. I now simply need to close that up, and I'll do a second right arrow and close the parenthesis, and now I can hit enter. I now have, for that one piece, I now have 8 times the factor s plus 5, and the s squared plus 6s plus 8, which you could probably have already seen, is factorable into s plus 2 and s plus 4. What I want to do now is actually obtain the partial fraction expansion representation of that, and the calculator has a function that will do that nicely for us, which is the expand function. Let me go ahead and clear on the calculator that input line. I will now go into the catalog of functions. F is pretty close to EX, so I will scroll up a few times, actually 3 up clicks with the cursor, to identify the expand command. I'll hit enter. That's now on the input line. I want to copy what I just computed, and so I do the up arrow to highlight that. I'll hit enter. It's now in the command line. I'll close the function expand with a right parenthesis, hit enter. I now have that piece of my expression, partial fraction expansion, equal to 12 over s plus 2 minus 4 over s plus 4. I can now put all of those pieces together to provide me with capital F of s equaling 5 plus, and that's the 5 that we divided out with the original first step, plus 12 over s plus 2 minus 4 over s plus 4. And that we can identify each of those particular pieces with their inverse time domain waveform, and we now have f of t is equal to 5 times the impulse delta of t plus 12 e to the minus 2t minus 4 e to the minus 4t, and all of that is true for non-negative values of time or for t greater than or equal to 0, and that is our answer.